Welcome to G Fun Facts Online. Today, we are taking a journey to the coldest place in New York City. In fact, it might just be the coldest place in the known universe. We are heading into a specialized, hum-free laboratory at Columbia University, where a team of physicists, led by Professor Sebastian Will, has achieved something that scientists have been chasing for nearly a century. They have created a Bose-Einstein Condensate, not out of simple atoms, but out of stable molecules. Now, I know that sounds like a mouthful of jargon, but stick with me. This isn't just a record-breaking temperature reading. This is the opening of a door to a new universe of quantum simulation. This is the story of how we learned to turn a gas of chaotic molecules into a single, unified wave of matter, a superfluid that flows without friction, and might just hold the secrets to everything from high-temperature superconductors to the interiors of neutron stars. To really understand the magnitude of this breakthrough, we need to step back from the complex equations and look at the nature of matter itself. In our daily lives, we are used to solids, liquids, and gases. But back in the 1920s, Satyendra Nath Bose and Albert Einstein predicted a fifth state of matter. They theorized that if you took a gas of specific particles, called bosons, and cooled them down to temperatures near absolute zero, something strange would happen. The particles would stop acting like individuals. They would lose their distinct identities. Instead of bouncing off one another like billiard balls, their quantum waves would expand and overlap, eventually merging into a single superatom. They would vibrate in perfect unison. This state is the Bose-Einstein Condensate, or BEC. It took 70 years to prove them right. It wasn't until 1995 that scientists finally created the first BEC, using atoms of rubidium and sodium. That discovery earned a Nobel Prize and revolutionized physics. Suddenly we could see quantum mechanics on a macroscopic scale. We could poke it. We could image it. We observed superfluidity, where this condensate would swirl in eternal vortices that never slowed down, completely defying the laws of classical friction. But here is the catch. Atoms, for all their utility, are relatively simple. They are point-like particles. They are essentially antisocial. In an ultra-cold gas, neutral atoms only interact when they practically bump into each other. Physicists call this a contact interaction. It is a short-range, billiard ball style of physics. While this was enough to prove BECs existed, it fell short of simulating the complex materials that define our modern world. In real solid materials, like the silicon in your computer chip or the copper in a power line, electrons interact over long distances via electromagnetic forces. To simulate these complex systems, physicists needed particles that could interact at a distance. They needed molecules. Molecules are the building blocks of chemistry. Unlike a solitary atom, a molecule is a marriage of atoms, two or more bound together, vibrating and rotating. Crucially, if you make a molecule out of two different elements, like sodium and cesium, the molecule often has an uneven distribution of electric charge. One end is slightly positive, the other is slightly negative. This creates an electric dipole. A gas of these dipolar molecules is a fundamentally different beast than a gas of atoms. Imagine the difference between a room full of tennis balls and a room full of magnets. The tennis balls only interact if they hit each other. But the magnets? They feel each other from across the room. They can attract or repel without ever touching. They can align. They can form structures. If you could cool a gas of these magnetic molecules into a Bose-Einstein condensate, you wouldn't just have a superfluid. You would have a dipolar superfluid, a substance with internal structure and complex behaviors that atomic superfluids could never mimic. This was the holy grail of ultra-cold physics. For decades, however, this molecular condensate seemed impossible. It was the problem of the sticky collision. To make a BEC, you need to cool a gas to mere nanokelvins, billionths of a degree above absolute zero. The standard method for this is called evaporative cooling. Think of it like a cup of coffee. The hottest steam escapes, taking the heat with it, and the coffee left behind gets colder. In the lab, physicists lower the walls of their magnetic trap to let the hottest particles fly out. The remaining particles collide, share energy, and settle into a lower temperature. But for this to work, the particles must bounce off each other elastically. They need to survive the collision. This is where molecules failed. For 20 years, every time physicists tried to cool molecules, the molecules would vanish. As the gas got denser and colder, the exact conditions needed for a BEC, the molecules would collide and disappear. Physicists discovered that when two molecules bumped into each other, their complex internal structures caused them to latch onto one another. They formed a temporary chaotic complex. They would stick together for a fraction of a second. In the quantum world, that is an eternity. During this brief embrace, they would either chemically react and destroy themselves, or they would be knocked out of the trap by a laser photon. It was a massacre in the vacuum chamber. The very complexity that made molecules so interesting was also their downfall. They were too friendly. They wanted to bond, and in doing so, they destroyed the experiment. This led to what some call the dark ages of molecular cooling. Experimentalists tried everything. They tried 2D pancake traps to keep molecules side by side. They tried electric fields. Nothing worked well enough. The loss rate was simply too high. The dream of a molecular superfluid seemed destined to remain just a dream. That is, until the team at Columbia University introduced a revolutionary idea: microwave shielding. Led by Sebastian Will, the team was working with sodium-cesium molecules. These are polar, stable, and theoretically perfect for a BEC, but they suffered from the same sticky collision problem. The solution came not from better cooling, but from better defense. If the molecules destroyed each other when they got close, the team decided to build a force field to keep them apart. They found this force field in microwaves. The concept sounds like science fiction. The idea is to bathe the molecules in a specifically tuned field of microwave radiation. Microwaves are just light waves with a long wavelength. When these waves hit the molecules, they interact with the molecule's rotation. The team used circularly polarized microwaves. Imagine the microwave field spiraling like a corkscrew. When this field interacts with a molecule, it dresses the quantum state of the molecule. It alters the energy landscape that the molecule sees. Crucially, this dressing creates a repulsive potential at long range. Normally, two molecules attract each other until they get very close. But the microwave field modifies this interaction. It induces an oscillating dipole that makes them repel each other when they are still relatively far apart, far enough to prevent the sticky collision from ever happening. Think of it like giving each molecule a bumper car suit made of light. When they approach each other, the bumpers repel. They bounce off elastically, preserving their energy and identity. They collide, but they don't touch. Let's walk through the experiment itself, because it is a masterpiece of precision. First, the team cooled clouds of sodium and cesium atoms separately, using lasers and magnetic fields, bringing them down to ultra-cold temperatures. Then, using a magnetic field, they carefully tweaked the interaction between sodium and cesium atoms, causing them to pair up into loosely bound pairs, known as Feshbach molecules. But these pairs were fluffy and fragile. To turn them into real, stable molecules, the team used a laser technique called STIRAP. This transferred the molecules to their absolute ground state, the lowest possible energy level for vibration and rotation. Now they had a gas of stable sodium-cesium molecules, but they were still too hot for a BEC. This is where they turned on the microwave shield. The effect was dramatic. The loss rate, the speed at which molecules were dying, dropped by a factor of hundreds. The gas became stable. With the shield in place, the team could finally perform evaporative cooling. They lowered the trap depth. The hottest molecules escaped. The remaining ones collided, bouncing off their microwave bumpers and cooled. As the temperature dropped, the team watched the density profile of the gas. At relatively high temperatures, the gas looked like a broad fuzzy hill. But as they hit 6 nanokelvins, a sharp peak emerged in the center of the cloud. A dense point where the density skyrocketed. It was the signature of a Bose-Einstein condensate. The molecules in that peak had stopped acting like individuals and had merged into a single quantum wave. The team pushed the temperature down to 5 nanokelvins. The condensate remained stable for nearly 2 seconds, a lifetime in quantum physics. So why does this matter? Why is a molecular BEC different from an atomic one? The answer lies in the dipole-dipole interaction. In an atomic BEC, atoms interact like people in a crowded dark room. They only know someone is there if they bump into them. In the molecular BEC, the molecules interact like people in a lit room carrying magnets. They influence each other from a distance. This long-range interaction is anisotropic. If you have two bars magnets, they repel if you put them side by side, but they attract if you put them head to tail. The sodium-cesium molecules behave exactly the same way. This means the properties of the superfluid depend on which direction you are looking. It is an anisotropic superfluid. This property makes molecular BECs the ultimate quantum simulator. A quantum simulator is a system that can mimic the physics of another, harder-to-study system. For example, consider supersolids. One of the most exotic phases of matter is the supersolid. It is a paradox. It has the crystalline structure of a solid, with atoms arranged in a grid, but the flow of a superfluid, flowing without friction. It should NT exist, yet it does. Molecular BECs offer a robust platform to study this. The long-range repulsion can force the molecules to arrange themselves in a grid, while the quantum coherence allows them to flow through that grid. Then there is the Hubbard model. This is a simple grid model used to understand how electrons move in solids. It is thought to hold the secret to high-temperature superconductivity, materials that conduct electricity with zero resistance at room temperature. Solving the Hubbard model mathematically for large systems is impossible for even the most powerful supercomputers. But a molecular BEC is a Hubbard model come to life. By trapping the molecules in a grid of light, physicists can literally watch how simulated electrons interact over long ranges. The creation of the sodium-cesium condensate is just the starting gun. The Columbia team and others around the world are already looking at what comes next. One immediate goal is to flatten the condensate into 2 dimensions. In a 2D pancake trap, the dipolar interactions become even more interesting. If the dipoles are perpendicular to the plane, they all repel each other side by side. This creates a stiff, strongly interacting fluid. If they are tilted, you get a mix of attraction and repulsion that leads to striped phases, density waves that spontaneously appear in the fluid. There is also a massive implication for quantum computing. Molecules have rotational states that can be used as qubits, or quantum bits. Because molecules can interact over long distances, you could theoretically entangle qubits that are not right next to each other. This connectivity is a huge advantage for building quantum computers. The stable molecular BEC provides a pristine, ultra-low noise environment to initialize and control these qubits. Furthermore, there is the hope of using these systems to test fundamental symmetries of the universe. Some theories predict that the electron might not be perfectly round, that it might have an electric dipole moment of its own. Searching for this in heavy polar molecules is one of the frontiers of particle physics. While the BEC itself isn't directly used for that search yet, the mastery of molecular control developed here feeds directly into those precision measurements. The creation of the first molecular Bose-Einstein condensate is a triumph of persistence. It represents the victory of control over chaos. For decades, the natural tendency of molecules to collide and react was a wall that physics could not breach. By using the microwave shield, by dressing the molecules in light, Sebastian Will and his team turned that wall into a window. We now stand on the edge of a new frontier. We have a fluid that flows without friction, interacts over long distances, and responds to the orientation of the universe. It is a state of matter that Einstein predicted, but in a form he could scarcely have imagined. From the mysteries of superconductivity to the inner workings of neutron stars, the answers may effectively lie floating in a small vacuum chamber in New York, cooled to 5 billionths of a degree above absolute zero. The age of molecular quantum matter has begun. Thanks for listening to G Fun Facts Online.